Hello and welcome. In this closed process problem, we have a combustible mixture of methane and oxygen, methane and oxidizer, which is 20% excess air in a rigid tank. So the total amount of the mixture is 1 kg, and then we have complete combustion using the NIG model, that is variable specific heat. We are supposed to find the adiabatic flame temperature, that is the final temperature of the products, as well as let's find the final pressure, for example. So the test step for this particular problem obviously is we'll follow the closed systems specific branch, and combustion and chemical equilibrium is handled in this node. In this case, we have premixed combustion, obviously, and variable specific heat means NIG mixture model. It's possible that a closed process problem could be non-premixed. Suppose you have fuel and oxidizer in two different tanks, which are the subsystems of a closed system. And in this particular case, we have a single tank, so we have premixed gas, premixed mixture. So let's first set up the reaction. Methane is reacting with, so in this composition panel, we first select the fuel. Its fuel is already default here. We don't care how we select our components, by kilogram or by kilomoles. As long as we can balance the reaction, we are fine. So 1 kilomole of, sorry, I should have picked, let's remove that, methane. So we have added 1 kilomole of methane. Here would be the reaction showing up, methane. Now we have to define the oxidizer. As a matter of fact, this is such a standard reaction, we can directly go and say that it's a reaction with air, so it's not theoretical, but it's with reaction with excess or deficient, complete combustion with known excess deficient air. So that's should be our chosen action, and we have 20% excess air, so lambda is 120%. With that, if I execute, you will see that the reaction is completely balanced, and of course you can switch through fuel, oxidizer, and products panel here to see the details of each gas mixture. Well, in this case, look at the products. We have 346 kg of products. Of course, that must be same as the reactants, which are made of methane, which is 16 kilogram, and fuel, which is oxidizer, which is 330 kg, 330 kg. So we have altogether 346 kilograms of the reactants, which becomes 346 kg of the products. But the question says that we have only 1 kilogram of the reactants. So we can choose an action that is multiply the entire reaction by a fixed, a constant. Multiply the reaction by a factor, which is 1 divided by 346. Now we'll have, if we execute this action, the reaction, as you can see, is now contains much less methane, much less oxygen, much less nitrogen. But if you convert them to mass, it'll be exactly 1 kilogram. Now that we have the reaction balanced, we go to the state panel. The state 1 is, as you can see, is keyed to reactant. If we select state 2, automatically it will go to product. So you don't have to mess with this part, just to take a look at it to make sure you have the right mixture. So state 1 is given 100 kPa and 300 Kelvin. Notice you cannot specify the mass. It will be picked up from the reaction panel. In this case, it's very close to 1 kg, as we expect. Products is, we only know by the way, the volume of the tank has been found here. So after the combustion, the volume of a rigid tank cannot change. So volume would be volume equals 1. And of course, mass is equal, but the reaction makes sure the mass is balanced. So it will be picked up here. What else do we know? Actually, we don't know anything else in this panel. If you think about it, we want to find the final temperature. We don't know the final pressure either. So with this information, we go to the process panel and do an energy balance here essentially. What happens is that we start from state 1, it's a premixed reactants, going to state 2 are the products. So if we solve the energy equation, notice what we know about the energy equation. There is no boundary work, it's a closed system. There is no heat transfer, it's adiabatic. And there is no other kind of work, obviously. So if I do a calculate, it should be able to find the specific stored energy of the final state and substitute it in the state panel for state 2. CE2 has been plugged in here. Now if you do a calculate, it should be able to find the adiabatic flame temperature as well as the final pressure, which is a lot higher than the beginning.